Okay. So thanks everyone for joining. We're honored to have Professor Onur Mutlu join us, give a talk. This is actually the first time I think we've met. And it's my understanding that obviously he's had some good relationships with some of us here at Qualcomm, and it was my surprise to hear that one of his students actually was an Innovation Fellowship winner in the past, which is great. That's always a positive for us to hear as part of the University Relations program. Without further ado, let me go ahead and hand it over to Professor Mutlu, and thank you for being part of the talk.
Okay, thank you very much, Adrian, and thank you very much for Ramesh for inviting me. Can people hear me? I just want to make sure of that. Everything's good? Okay, perfect. Then I will get started, I think. It's interesting. I feel like I'm teaching in my class remotely.
This is the new way.
This is a new normal, yeah. Okay, so this time, I think last time at Qualcomm, I gave a talk on in-memory computing, memory-centric computing.
Last year.
That was, I think, 2 years ago.
2 years.
I'm not sure if it was last year, probably. That was right before the pandemic, or maybe in the middle of the pandemic sometime, yeah. Yeah, it was in the middle of the pandemic, yeah, I remember. I decided to, Ramesh and I discussed that, we decided maybe we'll do something different this time, and that's why I'm going to talk about RowHammer today. And hopefully it'll be fun. Feel free to ask questions. Let's get started. So when I think of RowHammer, I think of infrastructure that we built. And this is one example of infrastructure that human beings have been building for decades. Well, not decades, sorry, thousands of years, like bridges, right? And if you get a bit flip in this infrastructure, this is what happens. You get a safety, security, reliability problem. And this is the Galloping Gertie. It's a Tacoma Narrows Bridge. It doesn't exist today because this is what happened to it in 1940. And it caused a serious safety, security, and reliability problem. And we will get back to bridges later on. But today we're building infrastructure that's much more important than bridges, I would argue. Computing infrastructure is everywhere. And it's making decisions for us. It's going to make even more life-critical decisions for us going into the future. Especially with self-driving cars, for example. I think this sort of bit flips are going to affect our lives much more. And I don't think we should really allow them to happen in an uncontrollable way, at least. This is another picture that I show actually to my students. I teach the bachelor's class at ECH. About 600 students actually take it in computer science. And basically I show this picture where people are building a city, San Francisco. And if a bit flip happens on the road they're sitting in, they will not be happy in a minute, basically. So I think of security in a very general way. It's really about preventing unforeseen consequences. And I think we should really hold ourselves to this standard going into the future. Can we somehow make our systems secure enough such that we can prevent any unforeseen consequence? Yes, I know it's very general, but if we can try to reach that standard, maybe we can reach a standard that's good enough for real safety and security. Okay, so with that prelude, what is RowHammer? RowHammer is the fact that you can predictably induce bit flips in commodity DRAM chips today. At the time we looked at this first time, we found out that more than 80% of the tested DRAM chips are vulnerable. And today, actually, it's even worse, as I will show you. What's interesting is it's really the first example, as far as we know, of how a simple hardware failure mechanism can create a widespread system security vulnerability. So it's the connection between reliability and security, if you will. And as a result, people are writing like popular articles that sound like this. Forget software, now people are exploiting physics. And I like this because this is really a nice high-level overview of RowHammer. It's really about physics in the end. And it's really about technology scaling, and technology scaling not going very well, let's say. And we knew that there were a lot of technology scaling issues in memory. This is an article that we were invited to write, and a talk we were invited to deliver at the International Memory Workshop in 2013. And basically, in this article, we argued that technology scaling is going to get much worse in main memory and memory in general. And we basically said, we need to somehow solve these technology scaling problems because they will lead to a lot of reliability issues. At that time, we were working about RowHammer, but we didn't really write it in this particular article. So if you're interested, you can take a look at it. By the way, International Memory Workshop is very heavily industry attended workshop. I'm actually delivering, it's happening next week. I'm delivering a remote talk on RowHammer. Essentially, this talk is going to be repeated over there in a tutorial this Sunday. Okay, so basically, we're going to talk about main memory. Clearly, technology scaling issues exist in any type of memory, but main memory is very special and interesting because it gets directly exposed to programming languages, and you interact directly with your language in main memory. And if you look at the fundamentals of main memory, it's charge-based. DRAM, dynamic random access memory, which has been around for about 60 years right now, starting with Dennard's seminal patent, is charge-based. It stores charge in a capacitor. And for it to work correctly, the capacitor must be large enough for reliable sensing, and the access transistor must be large enough for low leakage and high retention time. And all of the other structures, peripheral structures, need to work basically reliably. And as you reduce the size of the cell, the DRAM cell, both of these properties become difficult to maintain. Basically, reliable, you get into a lot of noise issues and reliability issues. And RowHammer is one reliability issue. It turns out it's actually very severe today. And we've been studying reliability issues in DRAM for some time now. This is one work that we have done with Facebook. We analyzed all of the memory errors that they have in their system circa 2013, 2014. And there's a lot of memory errors, a lot of servers. It's actually all of their production data center memory. And so you can actually draw some interesting correlational results. And this is one correlation result that I will mention. Basically, as chip density increases, server failure rate increases. Just chip density, this is the DRAM chip density. What does this mean? In denser DRAM chips, cells are smaller and closer to each other. As a result, they're more vulnerable to noise. As a result, you get more errors, and this reflects itself in the production data centers. If you're really interested in the definition of the server failure rate, we have it in the paper. I'm happy to talk about it, but we don't have time to cover this in detail. So basically, denser chips are more vulnerable to errors, essentially. And this is the paper that describes that data. And there's a lot more data, actually, on reliability of DRAM chips at a very large scale over here. Okay, we also were very interested when we started looking at the memory's technology scaling issues, very interested in analyzing DRAM chips in a more controllable way. Like in a data center scale, you're not controlling clearly because things are running in production. But can we control the access patterns, for example, to DRAM chips and figure out the mechanisms that cause the errors in a better way? So we built these FPGA-based infrastructures. The one on the bottom right is the first infrastructure that we built. And then we started building even newer infrastructure so that we can test these DRAM chips. And we did look at a lot of issues, actually, reliability issues, latency issues, etc. And this is one of the infrastructures. Okay, sorry.
Yeah, it seems like sorry.
Okay. You're stuck somewhere?
It get blurred out, but it refreshes though. Yeah. So I'm not sure what that is.
Is it because of me or?
I don't think so. See, let me show you. So there's a little bit.
Oh, okay. Yeah, I don't do that.
It's just the characteristic of.
Sorry.
That's fine. It could be related to exactly what you're talking about. But I think we're stuck with this. That's fine. We'll rely on the refresh.
Okay. Sorry, it's not that bad, hopefully, right?
I don't think so. Yeah, I think it's happening too. Okay.
Okay, so I'll continue then. Yeah, let me know if it becomes intolerable.
Sorry, just one quick question.
Sure.
You were talking about as the memory gets denser, the reliability goes down.
Yeah.
But earlier you talked about the security aspect of it.
Sure.
So are you going to relate at some point?
Yes,
to
absolutely.
reliability and security?
Absolutely, yeah. This is just a prelude, if you will. Yeah. So we wanted to basically test. So this is the infrastructure where we did a lot of RowHammer testing, especially. And we recently, well, 5 years ago, open sourced this infrastructure also. It's called SoftMC. People can use it. It has an easy to use API, C++ API. So if you want to do memory testing, you just need an FPGA plus our infrastructure. And people in academia and industry have been using it actually to discover new properties about DRAM chips. And we're going to release a new version of it that is capable of doing DDR4 testing very soon, probably this month. So we'd be happy to help actually if people are interested in using this infrastructure. Okay, it's a bit slow on my end also, by the way. So the reason we built this infrastructure actually was not RowHammer. The reason was to really study scaling properties of memory, and data retention, like refresh rates, was a big scaling issue in DRAM. And I will briefly mention that I will not go into a lot of detail over here, but we wanted to understand the retention time profile of different DRAM chips or within a DRAM chip. And if you look at the retention time profile, it's very heterogeneous because of manufacturing process variation in DRAM chip. So at the time we were studying, DRAM chips were refreshed every 64 milliseconds. And we asked the question, do you really need to refresh everything every 64 milliseconds? Because this is very energy inefficient and also performance and quality of service issues. And then there was literature showing that there's heterogeneity in DRAM refresh retention times for different cells, but we wanted to also see how this is scaling going into the future. And we did our own tests, and we basically confirmed that most of the cells do not require refresh every 64 milliseconds. Actually, you can reduce your number of refreshes by 75%. If you just look at this picture, right? Because most of the cells can retain data for 256 milliseconds, and you can actually increase your refresh period to 256 milliseconds. Of course, this is easier said than done because we, based on a lot of studies, we found out that this is dependent on the location of the cell. This depends on the stored value in the cell as well as the cells around it. This also depends on variable retention time, quantum-like effects. So it's not always consistent. Basically, it's random. So basically, we started doing a lot of research on enabling these heterogeneous refresh rates, if you will. And I'm not going to talk about that research. I think it's fascinating, actually. This is what the first paper we wrote with our infrastructure that shows an experimental study of DRAM retention times. And then later, we actually tried to solve the problems. For example, this one looks at error mitigation techniques, different types of techniques, online profiling being one of them. How do you solve the variable retention time problem? How do you solve the data pattern dependence problem? And how do you exploit application level properties like memory content? And here we tested LPDDR4 chips, for example, and we showed that the issues are becoming worse, like variable retention time is becoming worse. And more recently, we've been studying DRAM chips with on-die error correction capability and looking at what kind of error correction is employed and how can we actually reduce refresh rates in the presence of error correction codes. And these are some example papers that I'm not going to go into. And this is the latest paper that I will later mention. Again, using on-die error correction characteristics, we can design a memory profiler that can reduce the refresh rates and also identify uncorrectable errors as well. Okay, so if you're interested there, I find refresh fascinating, and there we have a lot of lectures on this topic. But that was the reason why we built this infrastructure, to study scaling issues. But while we were actually doing these studies, we were also quite interested in other errors, like retention time errors are very interesting, but read disturbers are also quite interesting. We had a very similar infrastructure for flash memory as well. I'm going to show that picture later on. In flash memory, we were finding there are a lot of retention issues as well as read disturb issues. So we asked the question also, are there read disturb issues in DRAM? And collaboratively with Intel, we studied this, and that is essentially what led us to analyze RowHammer. Okay, sorry. Basically, RowHammer, as I said, is the fact that you can predictably induce errors in most DRAM memory chips. And I already showed you that. The fact that you can predictably induce bit flips leads to a system security vulnerability, because you can figure out which bits can change based on the access pattern. And next time you basically make sure you allocate something security critical on that page, and you can take over the system, as we will discuss in a little bit. So let's look at the reliability phenomenon first. So what's the problem? So the problem is actually very fundamental. It's a read disturb issue.
So it's basically, so the errors happen in memory, but by controlling how to induce the errors, you're creating a security.
Exactly, yes. Yeah. You can corrupt data, of course. That may not be a security vulnerability, but by controlling things, as I will show you, later works actually shown that you can place pages, like page table entries, into appropriate places that you know is vulnerable to errors, and then you can hammer that location, and then you can cause a bit flip in your page table entry that enables you to gain access to your own page table, write access to your own page table, the user load process.
I mean, errors are those errors bit flip, but by controlling where you want to flip those bits, you can create security.
Exactly, yeah. Okay, so the fundamental phenomenon is very fundamental in the sense that read disturb errors occur in all types of memories. DRAM is interesting because if you have read disturb errors in DRAM, it's directly exposed to your programming language and operating system. So that's the difference, I think. So what is the problem? Basically, if you want to access one row in DRAM, you apply high voltage to the word line. This is called an activate in DRAM. You open the row, basically. If you want to access some other row, you close the row, meaning apply low voltage to that bit line. Now, if you keep doing this repeatedly, high voltage, low voltage, high voltage, low voltage, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge, it turns out physically cells that are vulnerable and physically adjacent rows flip, meaning they lose their charge. Of course, you need to be able to do this enough times before the cells get refreshed. So it's a charge leakage phenomenon in the end. But there needs to be some vulnerability of the cells. So clearly this should not happen, right? Because we're not even writing to memory. Nothing should change in memory. We're not even reading from memory in this particular case. Well, you're activating. It's kind of reading, yes, but nothing should change. Let alone something else that you're not even toggling, let's say. So this victim row, for example, can belong to some other process. It could belong to the operating system. So it could basically corrupt data in some other process on the operating system. And if you could control that, you could actually do worse, as we will discuss. So basically, when we did our study, we showed that more than 80% of the chips that are out in the field from 3 major manufacturers, who are actually more than 95% of the DRAM market today, are vulnerable to this. And this is a scaling problem because we tested chips from before 2010, and we could not induce these errors on those chips because cells are far away from each other, cells are large enough. As a result, you cannot do enough activates to cause these bit flips within a refresh interval. But in cells that were in modules that were manufactured in 2010, you could. And you can see that all modules that were manufactured between 2012 and 2013 were vulnerable. And I'm going to show you more recent data from 2020, 2022 very soon, after we discuss these early results. Okay, why is this happening? DRAM cells are essentially too close to each other. They're not electrically isolated from each other. Access to one cell affects the value in nearby cells due to electrical interference between the cells and the wires, essentially. It's called cell-to-cell coupling or interference. A very simple example. There are actually multiple mechanisms, and there are nice device-level papers that look at the mechanisms for RowHammer that I'm going to refer you to a survey on. I'm not going to go into the device level that much. But basically, whenever you activate one row, vulnerable cells and adjacent rows get slightly activated as well because there's not enough isolation. As a result, those vulnerable cells and slightly activated rows lose a little bit of charge each time you hammer. And if you hammer enough times before the cells get refreshed, you can drain the charge in those cells that are vulnerable. As a result, you lose the value. So this has higher level implications, as I said. It's a reliability problem, but if someone can do this predictably, then automatically your data structures in the programming language, as well as the operating system, can get affected. And we'll talk about that in a little bit. So this is the program that we wrote and released. Yeah, please, sure.
Data structure and programming can get affected, but there are also the cost to the hammer.
That's true, yes.
Because your access patterns also depends on how you're accessing it.
Exactly, yes. And this is one example of the access pattern, actually, if you look at this. I mean, this is not a C-level access pattern, it's an assembly level. We crafted, of course, and we released it. Basically, what this program does, as a user-level program, it selects addresses X and Y such that they're at the same bank. And it basically bypasses the caches and bypasses the row buffers in DRAM. As a result, it basically ping-pongs activates to X and Y in the same bank. And if the chip is vulnerable, hopefully you'll get bit flips. And we showed that this program actually gets bit flips. And we actually showed that if X and Y sandwich one row in between, you get even more bit flips. And this is going to be important because this is called double-sided RowHammer. You basically have a victim row sandwich between 2 aggressor rows. And that's actually induces a lot more bit flips than single-sided RowHammer. And later, Google built on this work to develop their security attack with the double-sided RowHammer. Okay, so
particular users rows are adjacent. So that in other words, you don't allocate operating system or some other user's memory next to your memory. So if you keep hammering, you will be corrupting your own data.
So in existing systems, there is no, it's essentially everything is mixed in the physical memory. Different programs, different operating system, they're all mixed in physical memory. There's no, let's say, isolation between different programs and physical memory, because otherwise you will run into capacity issues in memory.
Okay.
Yeah, but we will see that I think along the lines of your thinking, isolating things is going to be one of the potential solutions, but it's going to be very costly in terms of memory space. Sure.
I have a question.
Yeah.
So in order for someone to exploit something like this, as you pointed out, first of all, it's not happening consistently and reliably. It's a statistical mechanism. The affected, the kind of the impact on the neighboring kind of victim rows. And secondly, the hacker would have to have a very detailed understanding where exactly are the kind of the DRAM cells containing the information that he wants to change.
Yeah. So first of all, yeah, go ahead.
How do we get all of these? I mean, I understand the statistics and kind of the hammer and victim rows, but how would somebody basically collect all that very detailed integrity of the information.
Mm.
And then actually that needs to be very reliably in that same place.
So I think maybe we'll defer this to later, but first of all, it's consistent. If a bit flips, if you can RowHammer a bit, you can do it again and again and again and again. So it's very predictable in terms of the location. You just need to know where to hammer. And yes, the attack is, let's say, you need to know what you're doing as a hacker, of course. But there are a lot of works that show that you can actually do it. I'm going to mention some of those. Maybe you can get back when we talk about that.
Okay, I'll wait.
Okay, sounds good. Okay, so this is what we showed in our paper. Basically, we tested Intel and AMD processors, and they were both vulnerable. There's nothing special about Intel and AMD as long as you have a good memory controller that can activate things fast enough. All of the memory controllers are essentially vulnerable, and later work actually showed that. Today, actually, it's even worse, basically, because at the time we tested, you needed to do only 139,000 single-sided hammers to cause a bit flip in the worst case. Today, we're at, in the worst case, 4,800 hammers because of technology scaling. I'm going to give you those numbers.
Between the refresh.
So you just need to do 4,800 activates between 2 refreshes. And you can today fit a million, more than a million activates, basically. So it's getting much worse, basically.
So is this work showing that the errors are basically something that we intended to inflict a specific kind of error on a specific bit cell? Or these are errors that are basically statistical, and basically we know what the memory read, and we just randomly inflicted that many errors?
I'm not sure if I understand the question, but basically you're accessing memory, right? You're activating some rows and you're flipping some bits around those rows, physically adjacent bits. Nothing, so you're not supposed to inflict any bit flips, right? In memory, you should not be able to change anything by accessing memory.
I mean, I would put it this way. You want to corrupt certain memory base.
Okay.
So you are hammering the adjacent rows.
Exactly. Yeah. Exactly. Yeah. If you want to corrupt, let's say, if you know that there's some security critical data somewhere, get yourself close to those rows, and that requires some effort, of course, from the hacker's perspective, and hammer those rows that are. Yeah. Okay, so basically one can take over an otherwise secure system this way. This is the paper that introduced the issue, basically. We said the first sentence, as you can see, memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses.
I'm sorry, one more question.
Sure, okay.
You say flipping bits without accessing them. So in fact, this also means that even if you don't have access to certain information, because you don't have,
Privilege, yeah.
privilege,
Exactly.
but you may have privilege, you may have access to the adjacent.
Exactly.
And then you can still hammer them.
Exactly, yeah, absolutely, yeah. That's the memory isolation breakage. I think you put it very nicely. You can be in you don't have any privileged access to change values to some row, but you have access to another row. Yeah, or you read it. Yeah, exactly. Yeah, I think this is very fundamental. Basically, we're breaking memory isolation. All kinds of virtual memory protection mechanisms are useless if you break this sort of isolation physically. And this is the first work that built on our work. This is Google Project Zero's work. And I would recommend, if you're interested in how to really take advantage of this as a security, it's a beautiful security engineering. They have a black hat presentation as well as this blog post. They basically, I'm going to copy and paste in the slide from their blog post. They basically learned about the problem from our paper, as you can see. And they built two, basically they replicated the problem on their laptops, and they built two working privilege escalation exploits. And one of them takes over the Google native client virtual machine. It's interesting, but the other is much more serious, in my opinion. It takes over the x86 for Linux as a user level process. So this is directly, these are all copy paste from their blog post. Basically, what they did was they were able to induce bit flips in the page table entries of the user level process. And what they were able to do is they were able to gain write access to their own page table as a user level process. And once you gain write access to your own page table, you can do anything to this because you know the page table structure. You can gain access to, and you know the operating system structure. You can gain access to anything basically in that system. Of course, this is easier said than done. It's a probabilistic attack because they do something called page table spraying. They fill the memory with a lot of page tables so that they can increase the probability of landing a bit flip at the right place so that they can gain access.
But the bit flip also is so you can control which rows you are flipping bits.
That's right.
but you probably don't have control on how many of those bits you are going to flip.
That's right, exactly, yes. But later works actually are smarter about that. They do some profiling of DRAM first, and then they try to find places that are really good for flipping, let's say. This work is a bit, it's the first work, clearly. It's a proof of concept, but later works are more sophisticated.
So this is the underlying mechanism, but of course, then the hackers have to know a lot more
Exactly, yeah.
details about what to do.
Exactly, yes. So it's not an easy attack, but if you ask me, it's probably easier than Meltdown and Spectre because you're really flipping bits in this particular case. Yeah. Yeah. Okay, so this is now known as the RowHammer vulnerability, and I like this anecdote from a famous hacker on the internet. He says it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you're after. I think this is a nice description. Let me give you some like pointers to papers that have basically built on Google's attack, let's say. This is from TU Graz. These folks essentially show that you could take over the system of a website visitor by doing this through the JavaScript engine. This is actually very interesting. I think one of the authors of this is actually right now in Qualcomm, Victor van der Veen. He did a lot of work on RowHammer. Maybe he's also in this talk, I don't know. If he's there, hello. But basically, this work from Vrije University Amsterdam showed that you could have it's basically, you could take over an Android phone. And what they did was they fooled the operating system to allocate page table entries of their own program to a place that they knew, or they profiled to and they profiled and they figured out is vulnerable to RowHammer. And they could do this deterministically because the Android operating system has a nice deterministic process of giving out pages, basically. And then they would hammer that page and they would take over the system. So this is actually, if you're interested in knowing how a hacker would go about, this is a good paper that talks about it, or talk to Victor, I guess. That's another possibility. So there are other works that show that you could actually accelerate these using GPUs. You could do this through the RDMA engines inside through the remote direct memory access interface in a data center, for example. And these folks actually did the same thing concurrently. Even if you cannot take over a system because it may be difficult, let's say, these folks more recently show that you can break confidentiality, meaning using RowHammer, you can read someone else's private data. You may not be able to take over the system completely. So it's also a privacy issue. More recently, these folks did not take over the system, but they showed that neural networks, inference engines, by doing this in a, let's say, slightly intelligent way, causing these bit flips, you can make their accuracy extremely low, even though without the bit flips, their accuracy is reasonably high, let's say. So it becomes a safety problem also, as you can see, right, at this point.
In this case, again, because of the nature of the neural network, there's huge amounts of data and all, you know, in close by areas, right? It's kind of easier to hammer bits, and
exactly,
as you impact the weights, your accuracies can go down.
Exactly, yeah.
I mean, the page table was a specific example that's
Sure.
security related, because you are dealing with critical system information. Here you have large amounts of data that are all packed into the memory somewhere.
Exactly.
If you keep hammering, you basically corrupt the.
Exactly, and that's what they showed actually. They just did it in a, let's say, methodical way. Yeah. So I think maybe security concerns, yes, so people can argue that it's tough to exploit, but this sort of neural network attacks are going to be much more dangerous potentially and much easier.
And I would say in this case, even inadvertently you run into this, because if your access patterns for this massive amount of network data is not done properly, you will be hammering rows. Right?
Yeah.
I mean, if you're accessing same rows over and over, again, bringing them in instead of, you know, if you are not paying attention to the bandwidth and all that, then you could be hammering certain data over.
Yeah, potentially, in a memory intensive program. Let's say.
And neural networks are.
Yeah.
If there is an error correction code or something stored somewhere, you got to hammer the ECC as well to ensure that the user program really realizes that, does not realize that it has been corrupted, right?
Yeah, absolutely. We'll talk about ECC, but yes, certain ECC bits are also vulnerable to hammering.
Yeah, that's correct. So I think the ECC considerations come purely from the memory structure, and as you know, the devices go
Mhm.
down in size, and then you are catering for those errors themselves, right?
Mhm.
RowHammer
So
is
what
kind
it
of
is that you have
another
to connect
effect
the
on top
data
of
as
it.
well as the ECC together in such a way that the user program does not realize that. Right? If you just corrupt the data alone and then don't hammer the ECC, that the data has been corrupted, and the user program will ensure that, oh, there is a ECC is not working correctly, and you wouldn't do the damage what the bad guy is trying to do, right?
Yeah, I mean, you may not have that much control to hammer ECC and the row that you're trying to hammer, and then get and then make sure that the ECC doesn't correct, for example. That may be difficult to control, I think. But you can still corrupt data in the presence of ECC. As I will show, you get a lot more errors than existing ECCs can correct.
And again,
Yeah,
depends on
wouldn't it depend on how many bits you flip?
right.
Yes, exactly. Mhm.
And ECC is designed for the original memory design and catering for only so much, correction.
Exactly. Yeah, it's designed mainly for software, basically, right?
I don't know how many.
Yeah.
At some point it broke.
Yeah, I will show you soon. Basically, you easily get more than 4 errors per cache line. Then ECC can correct.
I mean, you provision them for the channel or for whatever
Yeah.
errors you expect.
Mhm.
This is on top of that.
Exactly. Okay, very good questions. I'm going to skip this one, but there's more work basically. And this is a cartoonish picture, as you can see. Maybe this is a solution for the problem. Okay, so there's a lot more to talk about, but I will, we wrote this overview paper that was invited for the special issue on TCAD, where we just basically gave a survey of RowHammer across the stack, meaning architecture, security, device level, circuit level. I don't have time to talk about that, but if you're interested, you can take a look at this paper that talks about a lot. But now let me talk about understanding RowHammer, some of the studies we did to understand. And I'm going to borrow from this paper first, and then we're going to go into 2020, 2022, a little bit later. So this is the infrastructure where we did a lot of these studies initially. We tested 129 total modules from 3 major manufacturers, as I said. These are some characterization results. I'm going to focus on some of them. We already discussed a few of them. Let's talk about the adjacency. This is from the memory controller's perspective. From the memory controller's perspective, what is the difference, row address difference between the victim and the aggressor? And if you look at it, most of them are adjacent, but some of them are not adjacent. This doesn't mean that they're not physically adjacent. This just means that memory controller doesn't know what's physically adjacent and what's not, because internally, the DRAM does some remapping of rows for fault tolerant reasons. For example, if one row is faulty, they remap it to some other place, and the memory controller has no idea about that. So this is going to be important because this affects the attackers as well as the defenders, because defender cannot easily put in the memory controller, okay, I'm going to refresh the adjacent rows. Yes, you will cover most of them, but non-adjacent ones you cannot cover that way. Access interval. This is basically how frequently you activate the aggressor row. Something is not allowed, of course, based on the standard. So if you increase the access interval, meaning reduce the bandwidth to DRAM, clearly you can get rid of errors, but this is not a good solution because you would reduce your performance significantly. As you can see, you need to really, and this is old technology, by the way, this is we're talking about 2012 right now. You need to really reduce your back-to-back activate interval or increase your back-to-back activate interval very significantly to get rid of all errors. Exactly, slow down the hammering. We're going to talk about a more intelligent way of doing this soon, but you don't want to do it for every access, basically. Okay, refresh interval is another solution, and this is going to be the solution that's going to be employed by industry soon. So if you increase the refresh rate, clearly you can get rid of errors because you cannot do enough hammers to cause these bit flips. And at the time, we found out that you really need to increase your refresh rate by 7x to get rid of every single error we saw. Now that's a lot. You don't want to increase your refresh rate at all. Remember that we actually want to get rid of refreshes. We don't want to increase refreshes. This is actually fascinating to me because retention time, and RowHammer are 2 technology scaling problems in DRAM. Clearly, you can solve one by making the other one worse, but we don't want to do that. We really want to fix both of the problems. So refresh is a solution, yes, but I would argue that it's not a scalable and good solution, but it's going to be our only solution soon, and at least without changing the DRAM chips or memory controllers.
The example you mentioned is the trade-off between performance and security.
Exactly, yes. And here refresh makes it energy also.
The other one also slowing down
That's true. Yeah, that's also bad for energy. Yeah, you're right. All right, you're wasting bandwidth basically. Okay, so data pattern is interesting. As you can see, some data patterns are much worse in terms of the amount of errors they inflict. This is because the coupling is different. So you can see the row stripe errors patterns actually cause a lot more coupling. As a result, RowHammer is much worse. This is true for refresh also because those are also coupling based. So this is interesting. This is the difference between refresh retention errors and RowHammer errors. Basically, retention weak cells are not, have almost no overlap with RowHammer vulnerable cells because these are very different mechanisms. Even though charge leakage in the end happens, it happens in very different ways. In RowHammer, it happens because of electrical interference and some other mechanisms, whereas yeah, okay, I won't go into it, but there are a lot of device level papers that discuss those. Errors are repeatable, which makes it a security problem. Basically, you can induce this bit flip in this particular DRAM cell again and again and again. So you can profile the DRAM and do it again, for example. We're going to get back to this also, but as many as 4 errors per cache line when we tested this, and this was with single-sided RowHammer. So ECC, simple ECC cannot prevent all errors, actually. You need to increase your ECC, but that's probably not a good solution to this problem because ECC error correcting codes are very good at fixing random errors, and RowHammer that's definitely not a random error. If you over provision your ECC, you're actually wasting a lot of space in your DRAM. And as I said, double-sided hammering is actually much worse than single-sided hammering. Okay, so if you want to know more, this is the 2014 paper. More recently, I'm going to talk about this paper in a little bit. We showed that RowHammer is getting much worse. I'm going to give you some key conclusions based on this. And even more recently, we looked at more RowHammer dimensions. I'm going to talk about that also. And there's a paper that's coming up in DSN soon where we actually looked at the word line voltage effects. So if you can actually reduce the word line voltage, you can reduce the DRAM RowHammer vulnerability. These are all real DRAM chip studies, basically. Let me talk about solutions before we go into more recent works. So originally, we argued that there has to be 2 types of RowHammer solutions. Immediate solutions, you need to protect the DRAM chips that are out in the field. Clearly, you have limited possibilities because we don't have a lot of programmability in our controllers today, and certainly not the DRAM chips, right? But longer term solutions can be much more fundamental. There could be a wider range. And we propose both types of solutions. And I'm going to talk about Terra, which at the time was our idea of a best solution. But today, I think it's falling behind because RowHammer has gotten much worse. So we're going to talk about other solutions too. So these are, yes, please.
This was good for 2012 scenario.
I believe so, yes. But if the RowHammer vulnerability becomes much worse, Terra is not going to be, as we showed in our recent papers, it's not scaling, basically. Yeah, I'm going to mention that also. Yeah. So these are the solutions that we envisioned at that time. Make better DRAM chips, isolate things better, maybe use better materials. This is tough, I think. Otherwise, it would have been done more easily by now, but it's difficult. Refreshing frequently, we're going to talk about that. Clearly, none of these are desirable. Access counters, we're going to get back to it. Basically, can you count the accesses to a row and refresh adjacent rows or throttle? We're going to get back to this. I think there's been some recent research in 2020, 2021 timeframe that has made this better, but still we need lower cost mechanisms. And as I said, ECC is probably not a good solution to this due to, it's a very heavy hammer, basically, to solve a very predictable error. So what was done in industry as an immediate solution was basically increasing the refresh rates because you don't have any other option, let's say. So this is Apple's security patch. You can see that they basically mitigated RowHammer by increasing the memory refresh rates, and they were nice enough to reference our paper, as you can see over here. They don't say how much. Probably they increased by 2x. Even 2x is not that great in terms of energy consumption and power. But as we showed in our paper, most vulnerable chips, you need to increase the refresh rate by 7x. So it's a trade-off, basically. They close the vulnerability. They don't get rid of it completely. That's my guess. Okay, but this is what you can employ in existing DRAM chips. So our solution was probabilistic. The idea is very simple. Whenever you close a row, meaning pre-charge a bank, you activate one or both of the neighbors of the row probabilistically. And you can choose your probability. It could be programmable. You can see that we did 5 out of 1,000 times. But if you're paranoid, you can actually increase that probability clearly. Clearly, there's a trade-off between performance and reliability guarantees based on the probability. But we showed that you get actually a very nice reliability guarantee, much better than hard disks if you choose this value based on the RowHammer vulnerability at the time. And this is nice because it's stateless, basically. You don't need to track anything. This is just a random bit flip. It doesn't even need to be random, according to what we said at that time, but we're going to get back to para. So at that time, it was an effective and low overhead solution. You can see it's low power, low performance overhead, low cost, low complexity. And you could do this in the DRAM chip as well as the memory controller. Both approaches were tried actually in industry today, as far as the ones I know at least. We will talk about the DRAM chip solutions later on, because we reverse engineered a lot of the solutions that were employed in DRAM chips. So some of them are probabilistic like this. So what they exploit is their slack in refresh. So refresh takes, for example, some number of nanoseconds, and not all of that is used for refresh. So you could actually induce some RowHammer fixing refreshes, let's say, inside the DRAM chip using para. That's what manufacturers do today. You could also do this in the memory controller, and that was our proposal. And our proposal was actually to cooperate between the DRAM chips such that you know which rows are adjacent at the memory controller. And it was actually employed by Intel. So this is an early version of RowHammer solutions that were employed by Intel. They called it PTRR, probabilistic TRR. And it's not exactly how they envisioned it. How we envisioned it was not the BIOS programmable. It was more dynamic, let's say. But in the BIOS, you can pick your RowHammer solution. You can either pick hardware RowHammer protection or 2x refresh. And hardware RowHammer protection is essentially a variant of para, where you pick your RowHammer activation probability, basically. That's the idea. And again, it has all the downsides of a memory controller-based solution that doesn't know the physical adjacent to the DRAM chip. So it closes the vulnerability, but doesn't get rid of it completely. Okay, so there's more, but you can find them in the paper. So I think the takeaway that I will hopefully reinforce more in the talk is, I think if you really want to solve these issues, you need more intelligent controllers. It's good for security and safety, but also other scaling issues like refresh. Like that was our conclusion with the retention times also. If you really want to get rid of refreshes, you need to have an intelligent control that understands the device much better. Okay, and I think we know how to build these intelligent controllers from the NAND flash. Yeah. Yeah. Yeah.
At the cost of performance, you could solve it.
Yeah, absolutely. Yeah, I thought that was a given. That's why. But I'm going to add it for the next incarnation of the talk. Certainly, I think performance, because memory controllers are designed for performance. That's why I thought it was a given. But yes, absolutely. You don't want to really give up performance also for this purpose. You want to give up minimally, let's say, because maybe you cannot do it without any performance loss, right? So we build these intelligent controllers on the flash side. So flash memory is interesting, and we did a lot of research in flash memory. These are some papers that are referenced over here. I'm going to reference one more. And that was one of the reasons why we wanted to study RowHammer and DRAM as well. So we built these controllers also. And if you look at flash memory, it's actually a memory that doesn't work off the bat. DRAM is supposed to work. Flash memory is expected not to work. So a controller makes it work. So I think what we envision is, I think DRAM needs to be a little bit also more relaxed in terms of the standards we hold it to. Maybe we should not expect DRAM to always work, but have controllers that make it work, just like flash memory. Of course, it's easier in flash memory because the latencies are much larger.
Just like the hard drive.
Exactly. Yeah. Exactly. Yeah. But
imperfect.
Exactly. I think DRAM needs to be thought that way. It's interesting that we've always been thinking of DRAM as perfect memory, right? But maybe we should really change that perception going into the future.
That was the question.
Yeah.
Is it possible to have a hybrid option on the refresh where you randomize the refresh rate? You're able to minimize a little bit more the security aspect.
Oh,
not always doing the same refresh rate.
For RowHammer
Yes.
solution, yeah, you can also randomize that probability that we mentioned in our probabilistic adjacent row activation.
So you randomize continuously the refresh rate. So you're still protected, but not all the time.
I see.
He's talking about randomization as against having a specific pattern from security perspective.
I see. Yeah. Yeah, you could do that. I think with our solution, you could actually add the randomization on top of it. Yes. And that may give you better guarantees.
But
yes.
it's not guaranteed.
Yeah, I mean, I think all of the issue with the probabilistic solutions is it's very hard to prove that it's guaranteed. So people have moved to deterministic solutions, and I'm going to talk about some of the deterministic solutions also soon. Sure. So this is, if you're interested in flash controllers, this is a paper that we were invited to write that covers a lot of really interesting issues in flash memory. I'll leave it at that.
Just one quick point.
Sure.
Now that you're talking about flash memory, and you just gave a talk yesterday on the MDM, I think there's a need to look at holistically at all different types of memory.
Absolutely, I agree.
From the system perspective, I'm putting information somewhere out in the network. and we need controllers
Yeah.
that understand the nature of each one of those memories and present the information back to you.
Yeah.
Reliably and securely.
Yeah, I absolutely agree, actually. I think but that also requires an intelligent controller again. If you have, let's say, the controller has access to all different types of memory, and it can trade off some of the reliability problems in one memory with some performance or some other, some benefits from some other memory, right? It can make up for the reliability issues in DRAM, for example, by serving it from, I don't know, phase change memory. I'll pick that one. Yeah, I absolutely agree. Okay, so there's more on RowHammer, and you can find them in our lectures. And we also have written actually shorter papers if you're really interested in. I think this is the shortest paper that we've written on RowHammer, but it's a bit dated right now, as you can see. And this is the retrospective that we were invited to write in 2019. Now I'm going to talk about what happened after 2019, because that is not covered in that retrospective paper. Even though it's very comprehensive, we're going to update that retrospective also at some point. But a lot of very interesting things happened in 2020 and 2022. First of all, we wanted to revisit RowHammer. We wanted to basically do the scaling study. What happened over the course of, let's say, last 8 years to RowHammer? So that's what we did in this paper that was published in ISCA 2020. And basically, we tested more than 1,500 DRAM chips from different generations, different types of DRAM as well. This is the takeaways very quickly. Essentially, newer DRAM chips are much more vulnerable. You get more bit flips due to hammering, and they're happening earlier. And earliest ones we could find was there are new chips whose weakest cells failed after only 4,800 double-sided hammers. So that's very quick, basically. Almost benign applications may cause this. So this is something to think about. Can benign applications cause RowHammer going into the future much more easily? Maybe we're getting there. Chips of newer DRAM technology nodes can exhibit bit flips in more rows, as well as farther away from the victim row. So there's a weaker effect as you go farther away from the victim row, but it still is there. And maybe even more importantly, existing mitigation mechanisms are not effective at future technology nodes because of the scaling problem, because basically what we thought was very effective para is not going to be effective because it caused a lot of performance degradation. You need to do a lot more refreshes if you need to refresh to make sure you overcome bit flips due to 4,800 hammers. So let me just quickly show you what I did. We don't have a lot of time, so I'll go through this quickly, but we have 3 different infrastructures. As you can see, this is one of the infrastructures. So we built a lot of infrastructure, and we did test many generations, as you can see, DDR3, DDR4, LPDDR4. Oh, okay, sorry. I can see it here, but I don't know. Okay, sorry. Okay. Okay, yeah, it probably takes some time. I don't know. Maybe it's the internet. I don't know. Okay, I moved it. Okay, now it came back, I think. Okay. Yeah, this is the table that shows basically lots of, yeah, I don't have time to spend, but if you're interested, you can take a look at the paper. Basically, we want to do this comprehensive study across many generations and many different types of DRAM to understand the scaling properties of RowHammer. And I'm going to present you some results. I already gave you the key takeaways, but this is one result, for example, that you can do with the infrastructures that we developed. You can see this picture. On the x-axis, there's hammer count. On the y-axis, you have RowHammer bit flip rate. And just focus on DDR4 old generation and DDR4 new generation. And for all manufacturers, consistently, as you go from an old DDR4 generation to a new DDR4 generation, the curve shifts from, as you can see, bottom right to top left. Meaning you get the hammer count to induce first bit flips become earlier, and you get more bit flips at the same time. So this is what we're dealing with, basically. This is a technology scaling problem. Okay, another picture over here. This is analyzing the first RowHammer bit flips per chip, divided by different manufacturers and divided by different technologies. And if you follow the arrows over here, you can see that newer chips from each DRAM manufacturer are more vulnerable to RowHammer because you get the first bit flips much more quickly, let's say. And you can see the distributions also over here. Okay, so I've already given you some numbers. There's more numbers, but you can find them in the paper also. There's a lot more study in the paper. I'm guess we don't have time to go over it. And there's actually, if you don't want to read the paper, there's also lectures that we have in our computer architecture class that talks about it. Now, let me also talk about what was employed by the manufacturers at that time. So I showed the Intel solution. I showed the Apple solution. It was good, I think, that the memory controllers were evolving, let's say. At some point, DRAM manufacturers said, oh, we solved the problem. RowHammer is done. But they didn't say how. So I'm not sure if they probably they didn't divulge the different information to the vendors also, but certainly they didn't divulge tell this information to the public. So we kind of took this as a challenge. And the question is it really secure? Basically, are these mechanisms, DRAM chips are advertised as RowHammer free? Are they RowHammer free? So we collaborated with people at Vrije University in Amsterdam who were doing a lot of RowHammer research, security side. And kind of we joined forces because you need the FPGA-based infrastructure to really understand what's going on in DRAM chips. But this trespass work showed for the first time that these, let's say, advertisements are not necessarily true, meaning DRAM chips advertised as secure are not secure. And we basically reverse engineered the solutions that are employed in DRAM chips just enough so that you could actually bypass the solutions. And the idea is this many-sided RowHammer attack. And at the high level, the idea is to hammer many rows, not just 2 rows or 1 row, hammer many rows such that you overflow the internal tables that exist in DRAM chips that are trying to count the accesses to different rows. And if you overflow those tables, then the DRAM chip is not able to count which rows are being hammered. As a result, you're back to square one, let's say. So it can actually cause these bit flips. That's the idea.
So from the security perspective, I understand that having worked around the solution, you can still find a way to cause the correction in the security information. But from reliability perspective, I think that solution does still improve reliability.
That's absolutely. I think so. I think the solutions still improve reliability because this is a more sophisticated way of causing bit flips, and it's not clear if existing programs have this.
I mean, if you really after it, you figure it out.
Exactly. Exactly. Yeah.
You break it.
Yeah, I agree with you.
Generally speaking, the reliability.
I believe so. Actually, I would agree with that. I think, although I'm not sure about the machine learning part. Yeah, I think that depends on how, I guess, how things are accessed, and because those are very memory intensive applications. I haven't seen a lot of works that looked at these more recent DDR4 protected chips.
Kind of second degree effect, right?
Yeah, probably.
Direct neighbors is a
Yeah.
more.
I agree with you. Yeah. Yeah, but I think taking the safety perspective, if you get a bit flip, like when you're self-driving car in the right, like not right moment, in the wrong moment, then it may be very bad, right? So from a safety and security perspective, this is bad, but from a reliability perspective, maybe it's not. Yeah. Okay, so basically we partially reverse engineer these solutions, and we provide an automatic tool that can effectively create many-sided RowHammer attacks. Okay, let me give you the idea. Basically, these are some different hammering patterns, basically many-sided hammering. You can see there are 3 rows that are being hammered over here. There are 4 rows that are being hammered over here. And we did a comprehensive study. So these are some examples from different modules. You can see that you don't get bit flips in this particular module in figure 10 on top left until you hammer 5 rows, because that's where you overflow the tables, for example. And it's actually not perfectly predictable, as you can see, because we didn't perfectly reverse engineer things. I'm going to talk about a later paper that almost perfectly reverse engineers things in a more methodical way. Okay, so this is the table. So we were not able to actually find a bit flip in every DRAM module, but we were able to find a bit flip in enough modules, let's say one third of the modules. And you can see that some of the patterns are 19-sided to get the best bit flips. It's interesting, basically. we later developed a lot more insight into this, as I will discuss. So you can actually do these in real phones. We tested a bunch of real phones over here, and you can see the check marks over here. That means that we found patterns that would bypass the mitigations. And I think this was enough for a proof of concept. But later we will have even better results, as I said. And attacks are actually possible, as we have also shown over here. These are some attacks that were published in literature, and you could actually do those attacks in these modules. So the key results I've already given you, basically. We showed a proof of concept where enough DRAM modules, enough mobile phones tested were vulnerable. And I believe these results were scratching the surface because the tool was not exhaustive. And there's a lot of room for uncovering more vulnerable chips and phones. And later, actually, Kaveh Razavi's group at ETH Zurich published some papers. I'm going to mention them later on. I'm not going to go into the details that showed basically you can do much better than what we showed in this early proof of concept. So the takeaway is RowHammer is still an open problem, and security by obscurity is likely not a good solution. So it probably is better to say, this is our solution, attack it. Can you actually break it?
So your recommendation is basically use whatever the DRAM manufacturer does, but still rely on an intelligent controller to
That's a good question.
deal with this problem.
Yeah, I'm not sure. I mean, we can discuss this more. I think a good solution, completely secure solution by itself could be enough. I mean, you don't have to use what DRAM manufacturers give you. As long as it's a completely secure solution, it could be done in the memory controller or inside the DRAM chip or in a cooperative way. I think we just need to solve the problem in a secure way, let's say. And I think there are multiple options here, actually. Now, on the DRAM side, one downside is the interface doesn't allow you to do much. Now, it's changed with DDR5. There's the RFM command, which is a bit of a mess also, in my opinion. But it's better than DDR4, clearly. But interface is still your limiter on the DRAM side.
So one just curiosity question. So from all this, I understand it requires some kind of adaptability in the controller.
Yeah, I think so.
Maybe use some AI kind of stuff in the-
So I think there are some papers that are being looked at that are trying to use some machine learning to understand these patterns a little bit more vulnerability.
Because also in general, for security, also we're looking at
Yeah.
whether we need in general for security solutions also,
Mhm.
some kind of
Machine learning, yeah.
adaptability and learning is required.
Yeah, yeah,
Because you can build defenses against known issues, but then
exactly. Unknown
what
issues you
keep
discover.
learning, what do you do?
Yeah.
You have to keep
Yeah.
learning, right?
Yeah, I agree. I think some reconfigurability or programmability and also combined with learning of what's going on inside your DRAM chip is really required. That's what I'm going to mention also later on. Yeah, because some other error may start happening, right? Or it may not be anticipated after 5 years in your lifetime, right? Okay, so there's more on trespass. We have detailed lectures, but this is the paper that showed that industry adopted solutions do not work. Okay, there's also the question we asked, how to guarantee that a chip is RowHammer free. I'm not going to talk about that, but basically the takeaway is we cannot guarantee it as far as we know today. It's a very difficult testing problem. And we did this work with Microsoft Research. We looked at a lot of different testing patterns on real systems, and we were not able to find a best pattern, basically. And I think this is very tough. Okay, let me talk about reverse engineering even more. So more recently, this was a work that was published at Micro. We basically were able to almost completely reverse engineer what was implemented in DRAM chips. I'm going to give you some insight into this, but if you really want to know, the paper is a lot more detail. And our goal was, again, understand whether TRR, the industry adopt solutions, are secure. How can we validate its security guarantees? So basically, we introduced this methodology, which we're going to open source very soon, that leverages data retention failures to uncover what's going on in TRR. And the basic idea is, so what is a data retention failure? If you don't refresh a row, you get a bit flip because of charge leakage, right? Now, in this work, we figure out which rows get bit flips at when, and we build on that understanding and couple it with RowHammer to figure out when an internal DRAM operation due to RowHammer issues actually refreshes that row. This way you can figure out when a row is refreshed because of a TRR mechanism. So by coupling our understanding of retention failures and how RowHammer behaves, we can figure out what's going on inside the DRAM chip. And there's a lot more detail, of course, to this than in the paper, but that's the basic idea. So you use retention failures as a side channel as to what's going on in the DRAM chip. And by doing this, we were able to essentially come up with new RowHammer access patterns. And we basically showed that all 45 modules we tested were vulnerable. And essentially 99.9% of rows in a DRAM bank experience at least one RowHammer bit flip. And we get actually up to 7 RowHammer bit flips in an 8-byte data bird, making ECC ineffective. So these results are actually much worse than even the original RowHammer paper, which didn't have any protection in the DRAM chips, right? Right now we have protection, but because we have uncovered what's going on, you can bypass all of those protections. So the hope is that this infrastructure can enable much more secure solutions in the end. You can test it against this infrastructure, right? Okay, so I will not have time to go over this, but I've given you the key idea. There's a lot more that goes into it. So if you really want to do these studies, you really need to set up an experiment to essentially exercise the chip and figure out what's going on. It takes time, basically. It's not easy. And for this, you need an FPGA-based infrastructure like we have developed. Okay. So, but okay, let me look at this table over here. So this table, these are the 45 modules we tested. You can see that the solutions that are employed by manufacturers are different, actually. Some of them are, for example, they detect the aggressors based on some counters. They count, for example, up to 16 rows. Some of them have per bank counters. Some of them don't have per bank counters. This is the ratio of regular refreshes versus RowHammer protecting refreshes. You can see that all of those ratios are different. The number of neighbors refreshed are different. So it's very interesting, actually. Some of them are more probabilistic. They don't have a big aggressor capacity. Some of them we weren't able to figure out by the time we published the paper, but if you put enough time, you will be able to figure out, basically. That's the idea. But the takeaway is, in all of the modules we tested, we were able to induce a lot of bit flips. And ECC cannot protect them. As you can see over here, we did a detailed ECC study. So you really need a very, very strong ECC to protect it. Okay, there's a lot more in the paper that I will not have time to go over, but I'm happy to talk. And again, Victor is a co-author of this paper. He knows a lot. Okay, I see. Yeah. Okay, so let me talk a little bit more about different dimensions of RowHammer. So this is also interesting because we didn't. RowHammer has different dimensions as well. So what are those dimensions? This is summary. We wanted to understand 3 fundamental properties. What is the effect of temperature? What is the effect of aggressor row active time? This is very interesting. If you keep the aggressor row active longer, it actually causes more bit flips because of some underlying device characteristics in DRAM. And what is the effect of variation, spatial variation, victim DRAM cells, physical location? And I'm going to give you some very quick results. And if you understand these better, you can, from an attacker's perspective, you can attack better. From a defender's perspective, you can defend better also, basically. It's good for everyone, basically, in the end. And again, using our FPGA-based infrastructure, we tested a smaller number of chips because these experiments take a lot of time because we tested actually a lot of temperatures as well. I don't know actually if I have those numbers over here, but basically they're yeah, sure. Sure, this one? Previous one, this one?
The 3 characteristics you're doing.
Okay, yes.
So aggressor row active time, is it the active time or is the frequency of activate, deactivate?
No, it's not the frequency. It's really the active time, meaning aggressor row is activated in the row buffer. You don't access it. You don't do anything. But how long do you keep it active before you do the next pre-charge and activate?
Right, but I think in the beginning we were talking about more frequently you
Yeah.
Hammer it, or more frequently you
Yeah, you get better. Yes.
You know that basically how you activate, deactivate causes and
that's right. But so over there, yeah, exactly. Over there, we did not study this.
Right, so this is additional.
This is additional, basically,
But
yes.
the frequency does matter.
Frequency does matter also, but this also matters, basically. Yeah, exactly. So this additional, yes. Very good question. Yeah. Okay. Okay, here we have 4 manufacturers, but again, this is an industry-wide problem. So the new manufacturer doesn't change the conclusions that much. So basically, these are the key takeaways. There are a bunch of other takeaways in the paper, but if I have to summarize, a RowHammer bit flip is more likely to occur for a given DRAM cell in a bounded range of temperature. This is very interesting because different cells have different temperature intervals where they're vulnerable. There's some explanation to the circuit level, but there's a new observation also. We still need to understand that. If the aggressor row is active for a longer time, you get even higher bit flips, meaning you keep the aggressor row active before you pre-charge and activate again, longer. Of course, there's a bound to the longer. And in certain physical regions of the DRAM module, you get a lot more bit flips. Okay, so let me give you some example attack improvements. So this was, if you activate aggressor rows as frequently as possible without basically activate pre-charge without leaving the aggressor row active for some time, you get some bit flips. But if you keep the aggressor row active for a longer time before you pre-charge it, you can actually get the bit flips much earlier. So you basically reduce the number of activations you need to do by 36%, which is interesting because if your defense mechanism does not take into account this one, you can actually induce bit flips because a lot of defense mechanisms operate based on when will you get a RowHammer bit flip. Is it 5,000 activations, 10,000 activations? If you set your defense mechanism at 10,000 activations and at some point you get 36% reduction in that, then basically you're again getting bit flips. Okay, spatial variation. again, because of design-induced or manufacturing-induced variation, vulnerability significantly varies within a chip, as well as across chips. The interesting thing is within, similar, you get similar values across subarrays. So I don't want to go into a lot of detail, but let's take a look at this picture over here. So this picture shows a minimum activation count to observe bit flips across different DRAM rows. These are different DRAM modules from manufacturer C. But you can see that in a given module, this purple module, for example, you have a huge variation in terms of the HC first value, minimum number of activations to cause a bit flip. So there are some rows that are extremely vulnerable. There are some rows that are not so vulnerable, let's say. And if an attacker knows this, they can attack better, right? And if a defender knows this, they can make their defense more efficient. Of course, now this requires chip level understanding, which makes both the attack and defenses harder. Okay, there are a lot more data that I don't want to go into, but columns exhibit something similar. Some DRAM columns are extremely vulnerable. Some DRAM columns are less vulnerable. So if you know this information, for example, what can you do? From a defender's perspective, this is actually real that we found, on average at least. 10% of the rows are very vulnerable, but remaining 90% of the rows are much less vulnerable. And this way, if you can somehow exploit this, if you know which rows are vulnerable by how much, you can greatly reduce the area cost of defense mechanisms, because your counters, you need to count less, let's say, for those parts. But of course, again, its complexity is higher still. This is another example here. This is also harder to exploit. So, for example, if some rows are vulnerable at some temperatures, if some other rows are vulnerable at different temperatures, you can disable the rows at their vulnerability windows. Again, I'm not suggesting this is a very practical thing to do, but if you develop a better understanding, you can potentially do this. Okay, and there's a lot more in this paper that I don't have, again, time to talk about. And we're doing more analysis, basically. And this is one analysis that is going to appear. We're working on the final version of this one. But basically, voltage swing on a DRAM row's word line calls RowHammer. And interestingly, no one has really studied this. And we did the first real system study, which requires building infrastructure where you can actually do this voltage changes on the word line. And basically, we showed that RowHammer vulnerability can be reduced via voltage scaling. This doesn't solve the problem completely, unfortunately, but it does reduce it. So that's the good thing is also it reduces your energy a bit. So it's a step in the right direction, but it's not a perfect solution. Now, that brings me to solutions. I think it's important to talk about solutions. I'm going to talk about one of our more recent solutions. We have some other solutions in the pipeline. But before I go into our solution, this is essentially an intelligent controller that doesn't require any cooperation from the DRAM chip. That was our goal, basically. Can we solve this in the memory control without any cooperation from the DRAM chip? I'm going to talk about that. But before we go into it, let's talk about the general solutions. I think the first solution is tough. More robust DRAM chips and error correcting codes. I think we can already dismiss that. Increasing the refresh rate across the board. We showed in our paper, it's very terrible, actually, as RowHammer vulnerability scales down to 4,800. And soon it's going to be maybe 1,000 hammers, right? Physical isolation, somebody mentioned this earlier. This was proposed in the literature. Isolate victim rows from aggressor rows, security critical data from non-security critical data, or different applications from each other. It solves some of the problems, but it doesn't solve within application problems, for example. And also people have shown that these are not robust. And also there's huge memory overhead in general, capacity overhead. Reactive refresh is actually employed a lot. Either Para, for example, does reactive refresh, right, probabilistically. Some other solutions were developed to detect aggressor rows deterministically and refresh adjacent rows. Graphene is one solution, for example. It's very interesting, but overheads are high. Proactive throttling is something that not a lot of works have explored, but you can do proactive throttling. So reactive refresh, one problem with the reactive refresh is you need to know which rows are aggressor physically adjacent. With proactive throttling, you don't need to know that. And the idea is, exactly, you slow down the hammering, but you do it intelligently in the sense that you figure out which rows are being accessed a lot, and you slow down the hammering only for those and not across the board. And that's what we do in our solution, basically. Even this this requires hardware cost. So it's not perfect in the sense that complexity and cost is there. So I think there's more need for solutions, in my opinion, because the solution space is, you're trading off cost, power, performance, complexity, and of course, energy on top of this. Power and energy are correlated somehow. But basically, we need better solutions, I think, going into the future. Let me talk about our solution. I'm not suggesting this is the best solution, but it has properties that are actually nice compared to some other solutions. And what we wanted to solve here was the scalability problem, because as RowHammer vulnerability gets worse, solutions become not scalable, as we showed in our earlier paper. And compatibility with commodity DRAM chips. If you take an existing commodity DRAM chip, can you attach our memory controller to it, and our memory controller will protect things. And yeah, basically that was our goal, efficiency and scalability without knowledge of or modifications to DRAM internals. And the idea is, as I said, selectively throttle memory accesses. So there are actually two components to it, and we're examining some future ideas based on this as well. One component is row blocker, and the other is attack throttler. Row blocker tracks row activation rates using Bloom filters. So Bloom filters are reasonably area efficient. And the idea is to blacklist rows that are activated at a high rate, and throttle activations targeting a blacklisted row. And basically the key, we have a security proof. If you actually select your parameters nicely, and if you know the RowHammer threshold, meaning how many activations you cause a bit flip, then you can guarantee that no row can be activated at a high enough rate to induce bit flips.
So what does the blacklist mean?
So blacklist means
You don't access them?
exactly, do not access them, do not activate them, not access them. If it's already activated, you can access it, but you're not going to activate it again. And there's some blacklisting period that is discussed in the paper.
Yeah, I mean, it has to be done
Refresh boundary.
by maintaining the program flow and. the
Exactly,
access,
exactly,
but just delaying the timeline there.
exactly, yes. Yeah. So you don't blacklist for a long time, basically. At least, I mean, in the worst case, it will be refreshed, and then you can remove the blacklist, right? Yeah.
Blacklisted and deleted.
Exactly. So we have a mechanism that tries to minimize the blacklisting. You can of course do better, I think, in my opinion. So we're gonna open source this code actually very soon as well, so people can experiment with it. Okay, the attack throttler. This is actually interesting because now you can actually look at the information in the based on this blacklisting and based on the activation rates, and you can identify which threads are doing the RowHammer attack. And you can feed this information back to the operating system, for example, and the operating system basically does some analysis on that thread, potentially, right? So that's one advantage I see in this particular thing. And we actually show in our paper that almost perfectly, I think actually it's almost perfect, you can identify RowHammer attacker threads. So you never identify something that's not an attacker thread as an attacker. But of course, this is based on some RowHammer threshold. If your RowHammer threshold becomes 100, meaning after 100 hammers, you cause a bit flip, there are a lot of real world applications that will cause a bit flip also. So attacker becomes benign as well. I think that's where we're heading in DRAM. Yeah. Okay, but basically this way, whenever you have an attacker, you can still get rid of the performance degradation and energy wastage because of the attacker. Because, okay, you solved the RowHammer security problem. This could become a quality of service problem now, right? If your solution is causing performance degradation. Now this solves the quality of service problem, hopefully. Now I think we need to still perfect the solution. So these are some results. Again, I don't expect you to look at them in detail, but we, for example, look at para over here and different solutions. And performance and energy overheads are negligible with BlockHammer. And you can see the thresholds we test over here. If you go down to 1,000 activations causing bit flip. And you can see that para is actually not so good. Its performance is not scaling very well, but our earlier papers show that as well. And if a RowHammer attack is present, we actually get even higher performance as well as lower energy consumption compared to state-of-the-art mechanisms because we can throttle the attack significantly. And we have a security proof, as I said, and this gets better hardware area scaling compared to existing solutions. Okay. And in this paper, we also classify 14 different mechanisms and different mitigation approaches. If you're interested, this is a nice classification of different mechanisms. And physical isolation, for example, as you can see, it has a lot of reds over here. Okay. Okay, so I think, I hope this is interesting in the sense that this is one example of an intelligent controller that can solve the RowHammer problem. And I think performance was a key constraint also for us in the design of this. Now, let me talk about what I will not talk about. Basically, there's a lot more that happened in 2020, 2022. So I'm going to basically flash some papers that people have looked at. So clearly there people are developing attacks and RowHammer solutions. There was a session at IEEE Security and Privacy on RowHammer purely. Major security conferences have this. Major OS conferences also have interesting RowHammer papers. But if you're interested, you can take a look at these papers. And this is actually upcoming, I think May 22, as you can see. There are 3 papers on RowHammer. I believe 2 of them are from Kaveh Razavi's group. I think this blacksmith paper, for example, is building on trespass, making it much, let's say, stronger without a detailed understanding of the underlying mechanisms. And there are solution papers, as you can see also. And the major architecture conferences have solution space explorations as well. This is HPCA over here. And there are also some interesting position papers that argue that we should be more transparent in terms of what's going on inside the DRAM. And we also recently released a position paper on this topic, not just for RowHammer, but if you actually know a little bit more about the reliability characteristics of DRAM, we can do really a whole lot more in a controller. This is actually what's happening in flash memory, I would say. Flash memory controller can figure out the reliability characteristics nicely because it has the mechanisms, whereas we're not there in DRAM for historical reasons also, clearly. Yeah. So I believe there's more to come in all of this, actually, hopefully. Or actually, I hope that we will solve the problem and we will not talk about RowHammer. But I mean, I think the read disturb is really fundamental. We will always be talking about read disturb, either as a reliability problem or scaling problem, hopefully not as a security and safety problem. I think we should really solve the safety and security aspects and relegate the rest to the reliability and scaling and everything else, right? Okay, if you have time, I will cover this future. I don't know what the time is exactly.
I'm sure there's folks that we've lost here.
Yeah, if there are questions, I'm happy to take them. The rest is basically some ramblings about the future and then conclusion, let's say.
Yes, I'm curious if you've done any work in developing an adjacency map so that you can remove things from your blacklist faster.
An adjacency map for like which rows are closer, like physically adjacent to each other. So we have not used that information in the RowHammer. So I think you're talking about the RowHammer blacklisting. No, we have not done anything. Our goal was really to prevent any potential bit flip. So not just a security solution, but reliable solution as well. Maybe I'm not understanding your question really well, though.
Okay, so my question is, you've gone through and you've said you're going to identify attackers, and you put them in a blacklist.
Yeah.
And at a certain point, you can remove them from the blacklist because neighboring rows presumably have been refreshed.
Oh, I see what you mean. Yeah, we have not done that. I think that's a good idea. If you know information about neighboring rows not being that vulnerable at that point. And also you can combine these solutions with proactive refresh as well. Yeah, but we have not done that. I think that's a good idea.
Yeah, that's where I was going.
Yeah, meaning they're refreshed. For example, if a refresh comes and they're refreshed, it doesn't make sense to blacklist an aggressor row that's physically adjacent. If you use that information, yes, I think you can make our solution much more efficient as well. But it comes with an overhead of the adjacency map, of course.
That probably goes for the case of adaptive refreshing. You already have some mechanism of refreshing some rows and not other. If you have regular refreshing, then you probably, you have the fixed pattern, when they're being refreshed. Right?
Yeah, exactly.
But once you have a solution and you are refreshing them kind of on need basis, then this information can be used on.
That's right. Yeah.
I think Victor has a nice comment here. Victor, you can speak if you want, but he says we'll solve all this in DR6.
Yeah, he's committed to fixing it out.
Okay.
Makes RowHammer look for what he's asking.
I hope so. DDR5 promised that also. maybe with Victor on board, it'll be. Yeah.
As long as it keeps shrinking.
Yeah, I mean, I hope so. I hope there will be some slight interface change to enable these solutions. We have some work that's ongoing that slightly changes the interface that fixes a lot of these problems much more easily. I'm happy to talk about it offline. Like slight interface changes actually can make some big difference. I'm not talking about RFM, but some interface change that gives DRAM a little more flexibility to do some internal operations. Right now, for example, DRAM has no breathing room in the sense that it cannot do any internal operation by itself, right? Exactly, it's a slave. If it has some breathing room, it can say, memory controller, stop a little bit. Let me do my operation over here. Then I think you can solve a lot of these scaling issues more easily, let's say.
But then also, if you combine it with some of the in-memory review,
Yeah,
there will be kind of more stuff happening within the DRAM.
yeah, yeah.
You give it a bigger
Yeah.
variety of operations to do.
Mhm.
Probably have some more autonomy.
Yeah, absolutely. I think more autonomy helps multiple things, including in
So
memory
distributed
compute.
Control kind of stuff.
Yeah,
and-
yeah.
But I think the key going forward is all adaptive control.
Yeah, yeah, absolutely. I
You
agree.
cannot build fixed thing because
Mhm.
there is a whole variety of
Mhm.
memories you are dealing with. And depending on the applications you're running, the patterns are different.
Mhm.
You got to learn.
Yeah, absolutely.
Yeah.
I mean, regardless of where the control is sitting, the DRAM, memory controller, both, I think I agree that it has to be adaptive and learning and getting better all the time.
We still have over 40 people. It'd be great if you want to finish up. on-
Okay, I'm happy to finish up. Yeah.
Yeah, for those that didn't able to
I
stay with
think
us.
we have another question.
Okay, another-
from
sure.
Henry, sorry.
Okay, sure.
He says, have you looked at vulnerability variations across chips in a DIM?
Across chips in a DIM. So yes, we kind of did that in the Micro 2021 paper, and yes, there's a lot of variation across chips within a DIM. No question about that.
Yeah, I have a question. I didn't
Sure.
understand it from your slides. And you know, Boris, are you still online? Boris? Because you mentioned that the cells have some dependency, I mean, different vulnerability at different temperatures.
That's
I
right.
didn't really understand why.
Why?
Boris has looked at such effects of temperature on different. Maybe he's dropped out.
Yeah, so it's interesting. So some cells, for example, are vulnerable at 50 to 55 degrees, but not vulnerable in some other range. Some cells are vulnerable to 80 to 90 degrees and not vulnerable in some other range. So I cannot claim that we completely understand the reasoning. There are some circuit level papers.
So
That-
there's some variations in the device that
Exactly.
makes it
Exactly,
act
very
at different temperatures.
exactly. Yeah. So there's a range basically,
I see.
and you're vulnerable. You're not vulnerable outside that range, but you're vulnerable within that range. I think there needs to be more device level studies to really understand what's going on.
I was
Frankly,
asking somebody.
yeah. Maybe if you have some device experts, they may have some intuition.
Do we want to listen? Do you think about the
Absolutely. You
future?
want to close up? with
Yeah.
the
Sure,
future and,
Okay, so future. So basically, I mean, hopefully it's clear that there's more vulnerability in DRAM. And I think there may be other errors, they may be going unnoticed. Some others may already be slipping into the field, who knows? I mean, clearly RowHammer slipped into the field. Maybe there are some retention errors that are slipping into the field. Can they be exploited? I don't know. Read errors, write errors. I think it's good to really understand the implications of it. And it's not just DRAM, as we discussed earlier. There's flash memory. Maybe it's harder to exploit flash memory, but there are emerging technologies also, hybrid memories. I think we really need to understand. But again, I think I'll repeat what I've said. We really need intelligent and adaptive controllers to solve these issues. And they can avoid many failures and enable better scaling, hopefully. So this is, I think, a methodology to think about. I mean, we've been kind of practicing this in our research, but maybe we need to do it more rigorously. We really need to understand what's going on in our devices and predict the future. That's what we kind of tried to do, right? And this requires real device data for sure, I think. Simulations take you only some way because they cannot model everything. Yeah, reliable metrics is also important, basically. What is the reliable metric to shoot for? And then architecting, principled architectures with security as key concern. I think you should add, you can add safety and reliability over there as well. How do you partition the duties across the stack, hardware, software, controller, DRAM chip? I think we cannot give up performance and efficiency. And I think patchability in the field is really important. And the last thing is design and test. I think we need to design for security, and basically online testing, continuous learning of this is really important, basically. And that requires online testing, in my opinion, as the memory is in the field. And again, a lot of these principles are employed in flash controllers a lot. They do a lot of online testing, for example, to adjust the voltages, to adapt to the best voltages, to read the flash. Of course, they have a lot more time to do that as well. I think maybe DRAM needs a much more intelligent controller to do some things, but you need to do that at much lower latencies than flash, of course. Okay, that's why we've been building infrastructure to really understand, essentially, and that's true for flash as well. So let me go back to this infrastructure. This was a galloping Yardi. Human beings have been building bridges for thousands of years, but bit flips keep happening. Again, this is reliability, right? So you cannot control everything. As a result, bit flips can be deadly also in some of these. This is Minneapolis, this is Genoa more recently, and there could be more that I have missed. I think the advantage we have in computing is we can be patchable, right? Whereas in bridges, it's very difficult to be patchable, right? Patching the bridge. Whereas in memory controllers, DRAM, I think we need to be a lot more patchable, basically. I think this goes back to your adaptivity also. So we have an advantage compared to bridges, basically. The world is not that bad. I think computing is a lot more flexible. Okay, I think that was our argument actually in our, like I go back 10 years ago, going back to the Internal Memory Workshop. That's what we argued exactly.
One more point.
Sure.
And the computing itself is becoming more error tolerant.
Exactly, yeah,
It's
that's
not
true.
always precise. So
That's true, yeah. It's not like bridges, right? Yeah. Bridges, you have to be precise, I think. Yeah, I agree. So, okay, this is actually interesting. This is a paper that was written by Intel and Samsung at the same conference where we exposed RowHammer. And they were also talking about DRAM scaling challenges. I don't think these companies talk to each other much, but they wrote this nice paper where they also argued for something similar. But I guess in industry, it's difficult to make these realized, let's say. But their argument was essentially architecting controllers and DRAM together such that the DRAM issues can be solved. They didn't talk about RowHammer in this particular case because it was not publicly, let's say, exposed. But they did talk about retention time issues, for example. Okay, let me give you some final thoughts on RowHammer. This paper was published in IEEE Security and Privacy in 2003, and it's a beautiful paper. And this, I think, predates RowHammer, as you can see. The idea here was these folks from Princeton induced memory errors in a real physical machine so that they could take over the Java virtual machine or Microsoft.NET at that time. And the attack is very similar to what Google has developed in 2015. Now, the difference is the way they induced the errors. So here they had to have physical access to the machine. You can see the picture in this machine. They have a lamp. They heat up the memory and they induce errors. And they basically show that if you can induce errors with this physical access, you can take over basically get rid of all of the isolation properties of the Java virtual machine, take over the Java virtual machine. And I think this is very fascinating to me. Now, this is an interesting paper and a lot of interest came about it, but security community really didn't go crazy about it. Why? Because this error is very difficult to induce, right? You have to have physical access to a machine. Now, what RowHammer did is enable those errors to be inducible by software, I think. So we're at a point in DRAM scaling that you don't need a lamp. You just need software that's inducing these errors. And that's what changed a lot of the mindset about these bit flips in the security community. It's very fascinating to me, actually. So essentially, the real chips are vulnerable in a simple and widespread manner, and this caused real security problems. And this hardware reliability and security connection is now mainstream discourse in the security community. As a result, there have been lots of papers that have been published in security and architecture venues for attacks. I believe there's more to come. Although it's getting difficult, of course, right? With protections in place, it's going to be difficult to attack. I think we need a lot more RowHammer solutions going into the future. Clearly, early solutions are not. Actually, the first people who picked up on our work were memory testing people. Memtest 86 folks included a RowHammer test in their testing programs. And then they started getting calls from people saying, I get errors in these RowHammer tests. So they actually had to write something on their website. But clearly, there are a lot of solutions, and hopefully we explore the solution space more. Okay, yeah, I think I already said this basically. But I think it's good that we're exploring hardware security issues a lot more today. And I think part of the cause is RowHammer. And it's interesting that two of the groups that discovered Meltdown and Spectre worked on RowHammer heavily before. So it's good that people are really fascinated about hardware issues, let's say. So in the security community, I think hardware is becoming a lot more, let's say, hot and more interesting today. And I believe there's more to come. I think we really need to understand, because as I said, computing is the biggest infrastructure we rely on today. We really need to understand how to make it safe and secure completely. Okay, to conclude, memory reliability is reducing. Reliability issues open up security vulnerabilities, and these are very hard to defend against. RowHammer is a prime example. And I find its implication on system security research tremendous and exciting. And in addition to system security research, reliability research also is very exciting to me. The bad news is RowHammer is getting worse at the device level, and it's probably going to get much worse unless there's some like device level changes, material level changes that happen in DRAM, which is going to be costly, no question about that. The good news is I think at least we are really aware of the problem. We're really aware that hardware is easily fallible. We're developing both attacks and solutions, and hopefully principled models, methodologies, and solutions. So I think if you go back, compare the solutions that we developed 8 years ago to today, we actually have security proofs in our solutions, for example. That's the good part. We know that they're secure. The difficulty is overhead reduction, of course. Okay, so if you're interested, there's a lot more. And as I said, there's a lot more lectures as well. So I will thank people who supported this research. And most importantly, I will thank my students who have done this research. And you can see some of them over here. This was our first gathering, let's say, after the pandemic. You can see them over here. And we released some newsletters as well, as you can see over here. Okay, and if you're interested in this more, this is just to plug in our courses. We actually open source all of our courses. They're all live streamed. Oh, you haven't listened? Okay, that's great. And you're welcome to participate also if you're interested. So people have been. Okay, great to hear that. Yeah, we will keep on doing this, live streaming them, and anybody is welcome to attend and contribute, ask questions, basically. Okay, this is where I'll end. Thank you for the lively interaction, and I'm happy to chat more.
Any more questions on that?
And one more thing from the last slide you were showing.
Last slide.
With all the, acknowledgement.
Okay.
Just to let people know that we are also working with the professor.
Okay, this one.
SRC.
Yes, this is, SRC is over here.
Specifically on the security aspect of it, but we work with him. He has a number of projects on the AI hardware side. So we've been working. I mean, I've been liaison with this team for some time, and hopefully in the future you will have more projects.
Yeah, I look forward to that.
So we started working with the problem he's doing is memory design center at CMU.
That's right.
Ago.
Yeah, 2014. Yeah, we had our meeting at that time. Exactly. Yeah.
But we continue this work through UR as well as through SRC. So yeah, there are a lot of avenues of working with him. So if people are interested in this or other work that Professor Mutlu is doing, let us know and we can connect.
Yeah, I actually did submit to SRC security call also. Probably you're not part of that, but there may be people who are interested in this.
This stuff is more on security.
Yeah.
That's why you're working with security tab.
Yeah.
But you do have work on the AI.
Absolutely. Yeah. AI hardware is ongoing, but if people are interested in security,
actually,
they're happy to.
Some of this stuff and tune it more towards AI and then become relevant to AI.
That's also true. Yes. Maybe we can discuss that for the next call. But yes, I think I'm very interested in especially the neural network aspects of this that people have been looking at.
But in general, memory architecture for AI itself is a large field. There is so much to do there.
Sure, absolutely.
Because it's such a memory-intensive application, reliability, security, all the issues can come into that one application domain, and there is so much to do.
Yeah.
Again, like I said before, combination of different types of memories, how do you manage, what information you keep, where, etc.
Yeah.
Sorry, question from people?
There's a lot of information on your slides. If I get a sanitized copy of the slides, would be great.
Yeah, I'm happy.
Those internally. So.
Sure. I'm happy to share everything. This is all public. There's nothing confidential, so I'll send you the slides right away whenever.
So, Victor, a question here. What lower bound of RowHammer threshold do you think is realistic? I feel that 1K is very pessimistic and will likely create lots of other issues. Are we really going to scale DRAM that much further?
That's great question. And I don't know the answer, but so far we've been keeping on scaling DRAM and the issues are getting worse. Refresh is also getting worse, clearly. Now we're at higher refresh rates, especially at high temperatures, right? We're at 16 milliseconds. And in some cases, maybe even 8 milliseconds, every 8 milliseconds. So I think people will push scaling it because capacity improvements come from that, right? And people are still very hungry for capacity. Yeah, because data set sizes are growing.
Capacity, high bandwidth, everything we're still pushing.
Exactly, yeah.
And all of those things, more you push them, more you're going to compromise on the.
Yeah, reliability issues will increase. But yes, I think at some point, like if you go to, let's say, 100 activations causing RowHammer, a lot of benign applications will fall into the RowHammer attack category at that point, and it becomes very. You do need to have a solution that's much more scalable than today, basically. Like today's solutions scale to 1,000, okay, but 100, I'm not. You really need to increase the hardware complexity and also energy compound. So it's an exponential curve in terms of scaling of the solutions. Yeah, I don't know a great answer. I mean, I don't think there should be a limit. We should try to solve the problems. But if DRAM capacity stops scaling, then we do need to look at other memories, which we've been looking. But unfortunately, none of the other memories seem to be at that level yet.
What do you think is realistic, though? That's the question. What's a good choice?
Well, I think what is realistic depends on the solutions we have at hand also. In today's solutions, I believe realistic is probably 1,000. My guess is, at least based on our simulations, we could probably go down to 1,000. But is that enough in terms of, like, do we declare victory at that point? I don't think so.
So I have a slightly different question for you. It's a little off the topic,
Sure.
but it's the other side of this coin.
Mhm.
So you are focusing on this bit flipping and how to deal with them, right?
Mhm.
So my proposal is, how about we look at how we are computing and look at computing paradigm that allows you to deal with that's happy with more bits.
More bits,
flipping.
okay.
For example, hyperdimensional computing.
Sure.
I have leverage of letting a lot more bits flip, and I still can compute what I need.
Yeah.
How do you think?
Yeah, I mean, we should be examining those paradigms that are more fundamentally, let's say, fault tolerant at the algorithm level, as well as execution model
At least
level.
for
No
certain
question about that.
application
Yeah,
domains.
absolutely.
I mean, it's not a
Sure.
generalized compute paradigm.
Yeah, I agree.
But at least for certain AI applications,
Yeah.
you just change the way you're looking at the information, and then
Mhm.
your reliance on the reliability of the memory goes down.
Yeah, absolutely. So I definitely agree. I think it's probably not going to work for every application, but for applications where it works, it could scale better,
I mean, those
basically.
applications that are heavy duty memory intensive.
Exactly. Yeah. So we actually had a similar idea. I mean, it's different, but maybe similar in the sense that we did this work on what's called refresh triggered computation.
Okay.
The idea is if your application has nice access patterns and you're going to touch all of the rows in memory, why don't you synchronize those access patterns such that you get rid of refreshes, basically.
Sure.
So that's one way of thinking. That's getting rid of the refreshes, which is a reliability solution, and taking advantage of the application's access patterns. So
Yeah,
I think we need to think about those things,
pattern,
basically.
I'm talking about
Yeah,
just representing information that doesn't rely on initial bits.
exactly. Yeah. Mhm.
And so I can allow 20-30% bits to be flipped, and I'm fine with it.
Yeah, sure. I think.
All right. Any last?
Yeah, thank you. Thank you for the questions also.